Good afternoon, Daniel. Good afternoon, Luna. Good afternoon indeed. Sorry, I'm a little bit late. Good afternoon, Jenna. Okay, let's just do this. Yes. Wait, good afternoon, Daniel. Good afternoon, Luna. Hello, Ashley. Good afternoon, Nikaya. Good, thank you. How are you? Even though I'm not really asking, but I sort of am. Good afternoon, but good, thank you. Good afternoon, Camilla. Hello, Jennifer. Oh, okay, that's who we are right now. Okay. I'm always a little bit more. Hello, Stephanie. Okay. I hate to be a little bit late on Thursday because Thursday is always a little bit more manageable day with better electronics and so forth. Hello, Amarani, and good afternoon. Yes, awesome, awesome. All right, we're gonna get rocking in a sec. Quick, like legit. Oh. Sorry. Okay, quick logistics. Hopefully I know that when I went to upload, okay, so quick logistics. We're going to get to physics here in a moment. But I noticed when I went to go upload the PDF from Tuesday's class from 2 days ago, I noticed it didn't take for some reason. And I noticed like the last two classes or the last one class or something, like it said class notes, but there was no notes there. So, and this is something that had happened months ago and Nikaya had noticed, but then we repaired. So just if anybody's tracking the PDF notes, I did fix them and they're all there to my knowledge, or let me know if anyone's missing, but they should be actually there. But for last class in particular, it's important that they're there, and it's important that you be aware of the PDF of notes, of lecture notes from last class, because the video did not work. I don't know if anybody noticed that, but no video was. And I just posted a thing in that section of Google Classroom that says there's no video, and it's a bummer because that was actually a fairly substantive class. I think. Good afternoon, Mariam. Good to see you. Good to see you. So there's no video from 2 days ago. Like there was a class, like if you weren't here, there totally was a class and it was fairly substantive and the material is important. Well, you know, I'll refresh you on it later or something, but you have to consult the notes on that. Right, that's what I'm talking. Well, that's what I'm talking about. Wait. So I'm a little confused. Wait. Well, so last week we did the Doppler. Okay, how am I gonna put this? Last week we did Doppler effect stuff, and there was a video of that, and that was important, and hopefully, and that worked hopefully. But then 2 days ago we did more. We did one more final chapter on the Doppler effect. Like it's not. I don't. Without getting too into this, like we did an. Oh, okay. So. And this is for everybody. No, I'm glad. Thank you. And you get points but for everybody, just to be as clear as possible, Doppler effect is a big topic. In principle, there's more than one case of the Doppler effect. And in my mind, it's very important to sort of, there's two things that are important. One is to be able to solve a Doppler effect problem in general, regardless of what case it is. And we have one method for solving all Doppler effect problems. And the one method works for any kind of case. And I do want you all to know it by the end of the semester, and you should be familiar with it. And you should understand that it works for any case. You don't have to like reinvent the wheel or something like that. And so some cases, I just expect you to be able to practice on your own and just check on your own with that procedure. But it's worth comparing and contrasting the results from different cases of the Doppler effect. And so we had done, and again, I'm saying this to everybody, there's a good question in the chat, but this isn't just about that. Like this is to everybody. We had done one Doppler case investigation last week, and then we did yet another one, and even another one, I think, 2 days ago. because ultimately what I'm trying to ultimately say, and I'm going a little fast right now because I actually want to move on to some other material today, but my ultimate takeaway from all this Doppler effect stuff is that the Doppler effect is a phenomenon that really, really demonstrates particular features of wave motion, and as opposed to particle motion. And it does so in sort of big, general qualitative ways that are noticeable and observable and dramatic, but it also demonstrates the particular, the specific nature of wave motion. It demonstrates it in a very specific mathematical way that is specific and concrete, but also very subtle. Like you have to know what you're looking at to see the mathematics of the Doppler effect. And so what I'm really trying to say is, as of the end of Tuesday's class, what I was showing you or attempting to show you what would happen in what we might call the fifth and sixth case of the Doppler effect. What would happen if we constructed a Doppler-like scenario for a stream of microscopic particles rather than the transmission of wave pulses. Sure. Hold on. I'm sorry. But I'm sorry. Can you guys? Sorry. Can you guys hear me? I'm sorry.
Yeah, we can hear you.
Okay. Thank you. Okay. So someone just requested a transcript, so I just did the transcript thing. So probably because they can't hear on their end. I guess that makes sense. But distracting me. So look, what I'm trying. I just have to be honest. I want to move on to a different topic today, but I want to be really clear what the conclusion of our last Doppler lecture was. Our last lecture 2 days ago. I'm really trying to say that if you really investigate, compare and contrast different cases of the Doppler effect, well, here's the takeaway. What you find if, and someone's here, pardon me. Okay, and again, this is gonna be my big qualitative summary now. You have to go back and look at the notes and look at the mathematical details to really see what I'm saying and to practice on your own, and like you do. But what I'm saying is, the Doppler effect, as it plays out in normal real life, say for sound, say for like a motorcycle passing you by on the street in New York City, like totally in other words, in realistic, good morning, good to see you. In a macroscopic, realistic scenario of the Doppler effect, like this kind of thing, right? Yeah. The basic point of the Doppler effect that I think you all get at this point is that if the source and or the receiver of a wave is moving relative to the medium, then the source and the receiver will disagree on their frequency measurements for that wave. Like that's okay. That's the fundamental point of the Doppler effect. Again, summary, not a trick. Like that's the point. Like, okay, so if I'm running toward you or you're running toward me, and one of us is sending a wave to the other, we're going to hear and measure two different frequencies for that wave. Okay, that's like the basic. Now, here's the subtle point. The subtle point that I tried to demonstrate mathematically on Tuesday. And then I'm summarizing now, partly because the video for Tuesday didn't work. Okay, I may try to find another one that I made semesters ago to replace it, but I might not be able to do that. I might ideally try to make a new one, but I might not be able to. So I wanted to be clear what we did Tuesday, because right now there's no video of it. Okay, what I tried to show Tuesday was that no matter what, the source and the receiver will disagree on the frequency of wave that's transmitted from source to receiver, as long as there's any motion at all relative to the medium. And they'll disagree, but they'll both be right. It's like a relativistic phenomenon. Each measurement is correct in its own frame of reference, and neither frame of reference is more correct than the other. Okay, Okay, like that happens in the Doppler effect. But here's the subtle thing that I tried to show Tuesday is that oddly, perhaps, if you, assuming all numbers to be the same, assuming all numerical values to be the same, if you have the source, say, moving toward the receiver, moving relative to the medium toward the receiver at some given non-zero speed, and you calculate the Doppler you calculate the Doppler effect, you find out what the frequency that the source measures versus the frequency that the receiver measures, right? So if the source moves toward the receiver at a given speed and you compute the Doppler numbers, you find certain numbers and you find a disagreement between the two frequencies. However, if the receiver moves toward the source at exactly the same speed as we just assumed, you find a different Doppler disagreement. Again, like you have to look at the specific numbers to really, I think, grok what I'm saying. But I'm saying, like, if you assume that the source measures a frequency of 500 hertz, and you see what happens, and you assume all other things the same, like sound 340 meters per second relative to air at standard temperature, pressure, whatever. If the source is moving toward the receiver at 80 meters per second while the receiver sits still, you get one Doppler effect. You get, instead of 500 hertz, you get something like, I don't know, whatever, 620 hertz. But if the receiver is moving toward the source at exactly that same number that we just assumed, say 80 meters per second or whatever, the receiver will not measure 500 hertz, nor will it measure the 620 hertz that I just mentioned. It'll measure something else like 605 hertz or something. Like the actual Doppler disagreement will be different, whether it's source moving or receiver moving. Qualitatively, they'll be the same. That is, if the source moves in, the receiver will observe a higher frequency than the source will. And if the receiver is moving in, the receiver will measure a higher frequency than the source would. Like the qualitative distinction is the same. So if you're just standing on the street in New York City and a motorcycle comes toward you, you'll experience like a higher frequency than the motorcycle hears. But similarly, if you're running toward the motorcycle, say at the same speed somehow, qualitatively, it'll seem like the same Doppler effect. Qualitatively, it doesn't make any difference whether the motorcycle is coming toward you or you're going to the motorcycle. Either way, you'll have a Doppler effect. It'll be in the same direction. It'll be the same basic effect. And that shouldn't really surprise anybody, because the whole thing about the Doppler effect is it's about relativity. It's all about the idea that whether the sun moves toward the earth or the earth moves towards the sun, it's ultimately the same physics, right? So, and I totally did, I'm going to look in the chat in a second. But what I'm saying that's interesting and really subtle is that if the source moves towards the receiver or the receiver moves towards the source, quantitatively, the numbers turn out to be different. Okay, and that's what I was trying to prove Tuesday. I'll look in the chat in a second. And then what I was really trying to show Tuesday, the really subtle or the really mathematical thing that is very testable, shall we say. Oh, no problem. Okay, great. And I'm going to look at the chat in a second, but I'm getting like headlines in the chat. Awesome. You're welcome, for sure. What we walked through Tuesday was, all right, let's pick all the same numbers again and do an entirely fresh case. Let's assume that we're throwing a bunch of tiny, tiny particles from a source to a receiver instead of a bunch of wave crests, okay? And if we throw a bunch of tiny particles, we will still get what appears to be a Doppler effect. That is to say, if I'm throwing crap at you while I run toward you, you're certainly going to get the crap, excuse my language, but if I'm throwing a bunch of little things at you while I run at you, they're certainly going to come at you more frequently than if I just stood still while I run at you, right? I mean, just picture it, right? Like, I think that makes sense. Or similarly, if I throw a bunch of stuff at you and you run toward me while I'm throwing, you'll certainly receive the stuff more frequently than I'm throwing it because you're running into it, right? Like, and that, so there will be like a Doppler effect. If you throw a bunch of little things, there will be an effect in that the source and the receiver will not agree on frequency if there's any motion at all of one or the other. So it will, like, qualitatively, again, look like a Doppler effect, but quantitatively, if it's particles, then whether I run toward you or you run toward me, we'll get the exact same Doppler shift. Like we will disagree with each other. If I'm running toward you, you're running, like source and receiver will disagree on frequency, just like in the Doppler effect, but they'll disagree in the exact same way. They'll disagree by the same amount, whether it's source moving or receiver moving. That's a very, like everything I'm saying now, like you can see, I'm struggling to say it. It's a very subtle point I'm making. I think it's subtle. It took me years to notice this, frankly. I mean, really. And it took me even more years to figure out an exact way to show it, like mathematically with these concrete examples. Like, to be honest, I mean, that's a, like it's not like, so I need you to look at them and look at them carefully. What we're ultimately saying is that frequency will be disagreed upon, but it'll be disagreed upon by a different amount, whether the motion is of the source or the motion is of the receiver, if we truly have a wave. And it will not be disagreed about on by different amounts. Like it'll be exactly by the same amounts, whether source moves or receiver moves. It won't make any difference whether the source is moving, the receiver is moving, if what we don't have is waves, if we just have a bunch of particles. And that is fabulous for two reasons, I guess. Okay, so I didn't mean to talk about this all period, but why that's so important is, number one, that means that on a very precise level, that's one way of testing whether what you have is a stream of particles or a stream of waves. And in some ways, all of our life, we're always looking for tests like that, because it's not obvious on a microscopic level whether certain things are particles or waves. And I'd like to revisit that if I can, but that's, you've heard that question your whole life, I think, as scientists, and it is a real question. Let me remind you, if I quickly as I can, why that's a real question. Because, all right, I'm going to say this quickly. I know I've said it before, but look, forever I kept hearing about that. When I was in high school, I heard about it. When I was in college, I certainly heard about it. Like, is this thing a particle? Is this type of motion particle motion, or is it wave motion? Is light particle motion or wave motion? Like, I got really bored of that question, as maybe you have. Right. And I certainly got bored and like annoyed when I finally got to a certain point in college, and they were like, you know, for centuries, first they thought light was a particle, then they thought light was a wave, then they thought light was a particle, then they thought light was a wave. And finally, in the 20th century, a bunch of geniuses, including sort of Einstein, came to this amazing conclusion that you would never believe in a million years until you take 14,000 physics classes. And the amazing conclusion is, it's both. Isn't your mind blown? That's how I felt about it. I was like, no, my mind is like totally not blown. This is like totally annoying, is what I thought. I thought you, right? Okay, thank you for responding. Oh, I should look in the chat too to see if I'm making any sense. I'm sorry. Hold on one second. Okay, it looks like I'm sort of making it. Okay, you're weak. Wait, I think that means you're laughing. Okay. All right. As long as I have your as long as it looks like at least two people are totally paying attention, I'm going to stay on this for a minute. Because, okay, so number one, everything I'm talking about right now was the point of the last class. But again, apologies, there's no video for it. That is partly why I'm like, I kind of wanted to move on in the material today, but the material we did Tuesday was super important. There's no video. Hear me again on that. I apologize. I'm bummed about it. But so you have to look at the notes for the numbers and how to crunch the numbers. But yeah, the ultimate conclusion is what we provided on Tuesday was like a test of how to know whether something is a wave or a particle, or not, or how to know whether some motion is wave motion or particle motion. And if you're laughing at all, like, yes, let me stay on this for a minute, because I hate it. Remember, I chose to be a physics major in college, like, right? Not just a forensics, like I was like literally a physics major in college. And then I went to graduate school twice after that. Like, supposedly I actually cared about physics. I mean, I do. And supposedly this wave particle question is one of the most fundamental central questions in the history of physics. It is. And yet I sat there as an undergraduate being like, can you annoy me more? Would that be like, are you guys through with this already? Like, Jesus, I really, excuse my language, please. I really was super bummed. I was like, you keep saying this. It's a wave, it's a particle, it's a wave, it's a particle. And you keep acting like all these geniuses throughout history have been all plagued by this. And like like Euclid says it's a particle, then, or it says it's a wave. Then, no, I guess he sort of said particle, whatever. Then Newton says it's a particle. Then Huygens and Hooke say it's a wave. And then and et cetera, et cetera. And then eventually your big point to me in the 20th century is it's like, it's both. And I was like, really? Like, no one thought of that before? Like, really? You're really telling me like, it could be vanilla, it could be chocolate, it could be vanilla, it could be chocolate, it could be vanilla, it could be chocolate. It's a swirl. End of story. Don't you feel dumb? And I was like, why? Why was that never an option before? Like, why are these the only two choices? Why can't it be both? Why did no one think of that? And why? And if it can be both, if it's both a wave and a particle, then why is that so interesting? And like, what? Like, why didn't you just say that from the start? We were wrong for a while, and now we're right. We found out it's both. Let's move on. Here's why. Okay, and I'm telling you, I thought it was totally stupid. And if you think it's totally stupid, I'm with you. I get it. It's mostly because of the way it's been presented. Here's why it's actually not stupid. The whole question, because when we say is a certain type of motion, wave motion or particle motion, it sounds like we're saying we're trying to squeeze it into one of two categories that we've just come up with. It sounds like we've just sort of come up with two categories, like particle motion or wave motion. And it sounds like we're just insisting that just because we've come up with these two categories, like it's got to be one or the other, and we're just like being like bullheaded about it, and that we can't even imagine that there might be a third category like called both. But that's not it. It's not like that. It isn't like chocolate or vanilla. It's not two categories. I thought it was. And the way it's often presented, it sounds like it is. It sounds like they're saying there's different types of motion. There's particle motion, there's wave motion, there's like other motion, there's like electricity motion, there's like this kind, and then there's like maybe kinds we haven't even thought of, but for some reason we're like pretending that would never happen. No, it's not like that. It sounds like that. It sounds like just different ways to describe motion, but no, here's the deal. Particle motion means, what particle motion from here to there means a thing goes from here to there. When we say something is not particle motion, when we say a type of motion is not particle motion, and we say it's wave motion, for example, even if there are other types that we haven't thought of, and really wave, that's a very specific word, wave, but when we say that sound travels as a wave, not as a particle, what we're saying is that there's no such thing as a sound thing. When we say that sound moves for, and I know I've said this before, but I want to like say it again now if I have people's attention and in light of Tuesday, even if this wasn't really the plan for today, but if you're going to get anything out of physics, like here's the deal. When we say, and also, by the way, this is why we're spending so much time on waves and why we spend so much time on harmonic motion, building up waves, and why the math gets so mathy. Because when we say that sound moves as a wave from my mouth to your ears, remember what we're saying is there's a whole bunch of air molecules between my mouth and your ear, or maybe if we're underwater, water molecules, or maybe if we're like in the middle of a guitar string, like string molecules. But we're saying, if we say that sound moves from my mouth to your ear, we're saying we already suppose that there's a whole bunch of some kind of molecules between me and you, some kind of particles are there, particles. We assume that there are a bunch of particles between my mouth and your ear, but that that a little particle near my mouth goes like up and down, or maybe like forward and back. And then the next particle goes up and down or forward and back. And then the next particle goes up and down or forward and back, right? This is the wave thing that we're talking about. Like we're saying that there's already a bunch of particles between my mouth and your ears, which we call the medium. And that little bits of this medium are moving in a very regular, repeated, cyclical, harmonic fashion over and over again in their little neighborhoods. Right? When we say it's wave motion, what we're literally saying is that a whole bunch of air molecules are required for this motion, but not one single air molecule ever does the motion. If I shout, and I know I've said this before, but in a way I can't emphasize this enough because it is the central thing of physics, or a central thing of physics, that when I send sound to your ear, I've definitely sent something. Like, I mean, you hear it, like, and you understand it, which is bizarre, right? And we can measure it, and we can measure the speed at which that happened and do all this physics on this motion that occurred of sound going from my mouth to your ear. And we can even say, oh, what was necessary for that sound was air molecules, like the medium was air. Air molecules were doing the motion. We could say, and we could do all the math of it. But you got to remember, the key point is that The thing that was moving was air. Air was necessary for the motion. The physics of air motion is like part and parcel of our belief in the physical reality of this motion, but not one single air molecule ever went from my mouth to your ears, right? The key of wave motion is saying that when wave, or whatever you want to call it, this type of propagation, pulse propagation, rather than particle trajectory, when something propagates from my mouth to your ear, it means something went, but no actual thing went. It's unthingy motion. When we say that sound, and we do believe it, when we believe confidently, we do all this math of sound being a wave, what we mean is something is required, such as air, for the sound to propagate through. But air is not sound, right? You can have a whole box of air and have no sound in it at all. And you can even have sound in things other than air. But you can't have sound with nothing. Like if there's outer space, right? If there's a vacuum, if there's no air, no water, no guitar string, like no medium at all, then you can shout as much as you want in outer space. And it is a truism that sound will not go from your mouth to someone else's ear, because sound is not a thing in and of itself. There's no such thing as a sound on, or like a sound particle, or sound, like no matter how close, and it's not just because our microscopes aren't good enough. It's not just because we haven't found one. It's that if you look really closely at the air, when you're sending sound through it, you find that you're not sending anything through the air. You're just having air ripple. Like, just like, if you all do a human wave in Yankee Stadium, it's only humans that are moving, but if a wave goes around Yankee Stadium, no human being goes around Yankee Stadium, right? So why I'm screaming about this now is to say, when we ask, is a certain type of motion, particle motion or wave motion, what we're really asking is, what's really happening is we're saying, wait, is it particle motion or not? That's what we're saying. We're not saying, is it vanilla or chocolate? And we've never thought of strawberry or swirls. We're literally looking at a piece of ice cream or whatever and saying, is it vanilla or not? And in this case, by vanilla, what I mean is we're looking at a certain motion and we're saying, is it particle motion or not? And here's the thing. If it is particle motion, that means the thing actually exists. And if it isn't particle motion, that means the thing does not exist. When we say that the motion of sound is not the motion of any particle, which is what we're saying there's no such thing as a bit of sound. We're saying sound is not an entity. It doesn't exist. It is a behavior, a phenomenon, a very, very elaborate behavior of a collection of things which themselves are not sound, i.e. or e.g. air molecules. Like, sound is not a thing. It does not exist in and of itself. It is an activity that a bunch of air molecules or water molecules or whatever can perform, right? That is a deep statement. So when we say that sound travels as a wave, we're saying sound doesn't exist as a thing, which I think is interesting. It's not a problem. It's just freaking interesting. It means sound is different from electrons. Electrons exist, like, as far as we're concerned, or, whatever you believe, like water exists. Hydrogen and oxygen together make water. That's a thing. Hydrogen is a thing. Oxygen is a thing. Put them together, you get water. That's a thing. And water can sit around on a table. It doesn't have to do anything to become water. It's a noun. It's not a verb, but sound is not a noun. Sound is a verb, if you know what I mean. It's not like technically a verb, but if you see what I'm saying, sound is a manifestation of a bunch of little things doing something. Those little things are called the medium. You cannot have sound unless you have a medium. So when people and the reason it behaves weird in a Doppler effect, the reason that the frequency, so I guess I am talking about this, sorry, but the reason that the frequency received is different whether the source moves or the receiver moves, even though it seems like that should be, what's the difference? Source going to receiver, receiver going to source, what's the difference? The difference is that it's not about a relationship between the source and the receiver. The difference is that when it comes to sound, there's this intermediary third agent called the medium, freaking air molecules, through which the sound is traveling. And actually, there is never a relationship between the speaker and ear. The relationship, the kinematic relationship, the velocity relationship that's relevant is between the speaker and the air versus the ear and the air. And for sure, like in other words, we're not contradicting relativity. For sure, if the speaker moves through the air at 40 meters per second to the east, then the air is moving to the west past the speaker at 40 meters per second. Like everything we believe about velocity and the symmetric relation velocity still holds true. It's just that we have to apply it to each object vis-a-vis the medium. The medium is making all the difference when a sound wave travels, or when any wave travels from a source to a receiver. The relevant relationship that then takes place and governs the math is source to medium, which is the same thing as medium to source negated, and receiver to medium, which is the same thing as medium to receiver negated. There's no relationship directly between source and receiver. Right. But if we send particles, if I just shoot a gun of microscopic particles that are so small that I can't even tell right away whether they actually do exist as particles, or maybe they're just a manifestation of some wave phenomenon, right? Because now to bring this full circle, like if I just had these tiny, tiny things that I couldn't see yet, but some phenomenon that I'm shooting and I don't know, are there things there or not? If there are things that I'm shooting, then source moving toward receiver is the same thing physically and mathematically as receiver moving towards source. Because if you're just shooting a bunch of little things, there's no medium. They are the things. They don't need other things to ripple through. So what I'm ultimately saying is that for years, when anybody said to me or in front of me, when they said that for centuries, people worried about whether light was moving as a wave or as a particle. And I thought, who cares? Like, okay, whatever. Like, so you don't know, like, is it, is a dog a Cocker Spaniel or is it a retriever? Like, whatever, it might be a Labrador. That was the wrong way to think about it on my part. And I do hold that. I think they presented it wrong too, many of them. But what they were really saying when they said for centuries, people have been worried about whether light moves as a particle or as a wave, what they're really saying is for centuries, people wondered, is light a thing or not? If we were to look closely at light, which is hard because usually we need light to like look at stuff, right? So, and like especially like before you could even imagine microscopes or anything else, you can imagine like just thinking about the question, if I were to break light apart, get like really into it and really look at it, would I find little bits of light? Or is it like sound where no, there's no bits of light, there's just a bunch of other things dancing around and making a phenomenon called light? When they're asking, is it particle motion or wave motion? They're really asking, is light an existent entity in the universe or is it a phenomenon? Is it a thing or is it a manifestation of lots and lots of other things? That's a freaking real question. I mean, it's really asking, does light actually exist or not? That's a freaking real question. And let me tell you, as long as I'm yammering about this at the top of my lungs, and it really is, like it's almost is the reason that physicists remain physicists. They want to know what the heck is going on in the universe. Like, never mind how do things move, like what is there in the universe? What is occupying space and time? And how do we look at everything? By light. If we don't even know whether light is actually part of the universe or not, like that's a head scratcher. So that when you get to the 20th, so if that's not enough, and I will move on in a second, but and I'm not trying to convince you of anything. I am trying to convince you that the question of whether light moves as a wave or a particle actually is an interesting question. I didn't realize that, but it is. And there's a reason that it keeps coming up. But the other thing is that if someone's actually saying in the 20th century that it's both, that is freaking weird. And it is not a surprise that no one said that before the 20th century, because saying that light moves like a wave and like a particle is literally like saying light exists and it doesn't exist. Like that actually is a contradiction. The reason people didn't think about it before the 20th century or think of that as an option, they might have, but they would reject it because that's not like saying ice cream is chocolate and vanilla, it's a swirl. Of course you can say that, but that's like saying the ice cream exists and it doesn't exist. Like what? Like what? And that's sort of what we are saying in the 20th. Like it is weird. And I'm not going to try to resolve that right now for you. I'm just saying it actually is why some people do physics their whole lives and never get bored of it, because It's freaking weird. And by the way, I'll say that, okay, I really will say this in the end. Yeah, it's totally a paradox. It's totally a paradox. And it's a paradox that we face looking at good, and thank you for, oh, wait, sorry. Oh, and I see that there's stuff in the, wait. Not a dumb, the thing in the direct chat, just before I get, not a dumb question, great question. No, wave motion can't be negative. Great question. I'm going to leave it at that for a moment just because I'm getting myself, but that's a great question in the direct chat. It says, in the direct chat, it says, I'm not going to read the person's name, but it says, I don't know if this is a dumb question. Can particle motion be negative ever? Like, can a particle move away from someone from a relative point? I don't think wave motion can be negative. Waves and particles can move in a negative direction. Like, direction is just how you define it. They could certainly move to the left just as easily as they move to the right. But what can't be negative about a wave, for example, is frequency. It doesn't make any sense to have a negative. We are assuming that in all these, you can't get a negative wavelength. That doesn't make any sense because that would mean like taking up less than zero space. So right, there are aspects of waves that cannot be negative. That is a really good point. But the direction of travel for waves and particles can be negative. So just the one thing I'm just trying to say now to everybody is, if anybody ever says that some kind of motion is both wave motion and particle motion, I'm not saying you have to right then resolve it, but just appreciate that is a weird thing to say. And the only reason we wouldn't say it as philosophers, it is because it's a paradox. And we don't go around saying that we believe in paradoxes just because we feel like it. We say this stuff as scientists because we think that we get evidence from the world that says it. And as scientists, what we believe, or as physicists, we believe that when in doubt, when we have a conflict between what the data and experimental results say versus what our own intuition or even our intuition about logic says, we're supposed to trust the data and the experimental results first and foremost. That's what makes us scientists. That first and foremost, we're trying to be honest about what the world of space, time, matter, and numerical evidence tell us. Like, we're supposed to first and foremost be respecting whatever comes in through our five senses. And we're supposed to be arranging our mind and our concept of logic and intuition around that, not the other way around. Is that necessarily right? I don't know. That's why there are also philosophers and mathematicians in the world. I'm not saying it's like, often we have conflict between logic and empirical evidence, and I don't know which one is supposed to hold sway when there's a conflict, but I do know that what makes us scientists is that we're saying, when we're acting as scientists, we're supposed to prioritize the empirical evidence and patterns as best we can. And there seems to be empirical evidence to suggest both wave motion and particle motion of light, which leads ultimately to the 20th century and a resolution called quantum mechanics, which is all very, very heavy and heady and mathematically hard, because it's conceptually hard, because at the quantum mechanical level, what the world seems to be telling us is stuff we don't want to hear, but it's telling us. So we have to listen. I mean, but that's why it's all interesting and continues to be interesting, even if you do it for years and years and years and years. So the class from Tuesday was meant to be a demonstration of how we could test for whether a small microscopic stream was indeed a wave stream or a particle stream. And the test is whether the two frequencies agree or not, whether source is moving or receiver is moving. Like, that's the ultimate takeaway of Tuesday. Again, okay, so that, and I appreciate that you guys were listening to that. Hopefully that makes some sense. We're going to move on. We're going to move on now. But what we're going to move on to is the next. I mean, I know we don't have very much time in the course left, but we're going to move on to the next example or subtopic of unthingy motion. Right? Ultimately, this class, if you find this class, Physics 2, is Physics 2 precisely because what we're here to study is all the patterns and principles of classical physics as they apply to unthingy motions, to immaterial, abstract, but nonetheless scientifically verifiable motions. Wave motion is the first example. Another example of an unthingy motion ultimately is the motion of electrical currents and electrical and magnetic fields. Okay, so that's what we're moving on to next. I know we don't have a ton of time in the class, but that's what we want to bring this all to is what about the immaterial motion of what we ultimately call electricity or magnetism, and or ultimately electromagnetic radiation, otherwise known as light. So I'm going to totally shift gears now. I'm watching the clock. I know we have a half hour today. I'm going to totally shift gears. I don't know if you've seen this in lab yet. At some point in lab, you're going to shift gears too. I'll just quickly ask, have you done anything in lab yet? You could just put in the chat. Have you done anything in lab yet at all with electricity at all? And it's okay if you have not. I'm just wondering. Not yet. Okay. Oh yeah, I knew that. You told me Tuesday. I'm sorry. But yes. Okay. So I'm going to, again, hopefully this will help you. I'm going to jumpstart you a little bit here so you'll be a little bit less thrown when you get to lab. I'm going to tell you at some point in lab, you're going to shift gears and you're going to start looking at simulations of electrical current, like circuits. So that will seem like a leap. I'm going to start you right now on electrical forces, electrical charge, electrical fields. And let me just tell you again, if it seems jostly, like it is really a shift of time. And for some of you, this will be a big relief. You might be totally sick of waves and all that, and that's fine. And the math changes here. So maybe this will be a relief, change of pace for some of you. But for any of you who are thinking like, wait, where's this coming from? What? Well, I mean, number one, it's the new chapter. But number two, the connection between all this material or among all these bits of material is that this next chapter is as I said a second ago, is a different version of unthingy motion, immaterial motions and phenomena in the material world. Okay, so okay, so the equation in that there's two equations on the board right now. Oh, let me look in the chat. I'm sorry, hold on. Oh yeah, okay, cool. Thank you guys. Okay, two equations on the board right now. The second one, I don't expect you to necessarily, I don't expect that you recognize the second one. It's like sort of where I'm heading with this discussion. And to be honest, I don't know that I'll get to the second one by the end of today now, just so you know. But it's like my goal is to get to the second equation. But I'm going to start with the first equation, which in some form or another, I believe you may recognize from chemistry. So I'm going to start with something that's maybe a little bit reviewish, hopefully, or at least a little bit familiar from your chemistry background. Okay, so I'm going to Okay, I'm going to turn the page. I was going to read this and then turn the page in a second. What I'm saying here is, okay, if you have any 2-point charges in the universe, such as an electron is a point charge. It's a certain amount of electrical charge, happens to be negative charge. It's contained in a volume that is so small, we regard the volume as infinitesimal, i.e. taking up nothing more than like a Euclidean point of space. Protons are also charges, although they actually take up a little bit more space. They actually take up some space, but they have an amount of charge that's equal to the electron, only considered positive. We'll get to that in a second. But anyway, if you have any 2 charges in space, such as electrons, if those charges are separated by a certain distance that we call R, if you call one of the charges Q1 and the other charge Q2, and they're separated by distance R, they will automatically and necessarily exert forces on each other with a magnitude that's given by a law, an equation that I'm about to. Yes. And I was just about to say that. Okay, very good, right? And I know we never actually went over it, but yes. So let me, right. So I'm about to write the equation down here and about, but yes, what Sam just pointed out in the chat, what I'm about to say is that any 2-point charges in the world pull or push on each other in a fashion that is precisely analogous, identical, in fact, to the fashion in which any 2-point masses in the world pull automatically on each other. The electrostatic interaction, the electrostatic force between point charges is just like the gravitational interaction or the gravitational force between point masses. It is like that in 2 respects. One, each of them, I'm going to write this down in a second, but each of them is an example of what we would call action at a distance. It happens automatically without touching. For an electron to push on another electron, the electrons don't have to be in contact. The electron doesn't have to be touching the other electron. The electron doesn't have to reach out and in any way physically push the other electron in order for this force to exist. So empty space can be between them and the force will still be there. Conversely, there could be stuff between the 2 electrons. There could be material, wood, glass, carbon, copper, whatever, air, water, between the 2 objects, and still they will push on each other the same way they would otherwise have in empty space. So in other words, charges pull or push on each other just like point masses pull on each other automatically through empty space by sole virtue of existing, right? So we call this action at a distance. This is an immaterial kind of interaction. It doesn't require any kind of thingy thing to go in between the 2 objects for this to happen. So that's one respect in which electrostatics works just like gravity. And in fact, and I'm glad Sam brought that up in the chat. And in fact, I'm going to say from here on in, any time I ever talk about electrons interacting with protons or anything, if you ever have any trouble picturing it, picture the sun pulling on the earth and or the earth pulling on the sun. Okay, so number 1 respect is that it's action at a distance. Number 2 respect is that the math turns out to be equivalent. And that's what we're going to write right now. Okay. So whether coincidentally or not, and it's not a coincidence, the two interactions of which we know it as of this moment right now, I mean, in this class, the fundamental interaction between 2 points of mass and the fundamental interaction between 2 points of charge, they both work the same way in that both are fundamental, both don't require any physical intermediary to make this happen. They don't require any activity or action. They just occur through empty space. And they're both inverse R squared relationships in that, in both cases, the farther away two objects are, the less they will pull or push. And specifically, the farther away they are squared determines the extent to which they pull or push. I say pull or push. Notice there's positive and negative signs going on here. Notice with, you may want to make a note of this. I don't want to crowd this page, and I'm going to go on in a second. But from here on in, from here on in, negative means pull and positive means push. You'll see why when we get into the vector nature of this, but it actually sort of makes sense. And again, I know you've had chemistry before, so none of this is shockingly new, hopefully, but protons are considered positive charge, electrons are considered negative charge. And you know from experience in chemistry and so forth that for whatever reason in the universe, and I don't know, but likes attract and I'm sorry, likes repel and unlikes attract, right? So it actually sort of makes sense. Like, so I'm saying if you have any two charges and they're somewhere separated by a distance r, they pull or push each other in an amount that's determined by how big each of them is and determined by how far away they are squared. But here's the thing is that if both of them are positive, they multiply to, if both Q1 and Q, so I'm looking at the top equation on the top of the sheet. If Q1 and Q2 are both positive charges, then you have a positive multiplied by a positive. The whole answer will be positive, and we consider that a push. Each one will push on the other, shove it away, repulsion. If both of them are negative, same thing. A negative times a negative is a positive. They'll push on each other, repulsion. But if either one is negative while the other one's positive, a negative times a positive is a negative, they'll pull on each other and you'll see the sign of the whole thing is negative. So in general, so that like system works out nicely. It's just a nice way of keeping track of things. So negative means pull from now on and positive means push. And with masses, all masses are always positive. All masses are always positive. But so we multiply a positive by a positive, we get a positive, but then there's a negative sign in the equation for gravity, technically always there to say that it's always going to be a pull, if that makes any sense. But all right, let me go on with numbers. I think, yeah. So good question. So good observation, Sam. So now, so just like with, Okay, just to either say or to remind you or whatever. If you so what this says is with gravitation, M1 and M2 stood for point masses, two different, right? Any two arbitrary two masses that were both points in the sense that they were assumed to take up very, very infinitesimal amounts of space, but they could each be a different magnitude of kilograms of heaviness of mass. So M1 was a big mass, M2 was a small mass, and they're each measured in kilograms. And then so you multiply them both together, and the bigger either one or both is, the bigger the result of the numerator is, and you divide by the square of the distance between them, and now you're on the verge of having the result. But then you take that whole package. Again, I would go back a page, but just in case people have to copy this down, you know, the force of gravitation exerted by one mass on another was the mass of one in kilograms times the mass of the other in kilograms divided by the square of the distance between them. And then that whole package is then multiplied by a universal proportionality constant. Like universal meaning it's always this one number. You don't have to memorize it. You can always look it up. It's always the same in all examples. This one number, capital G, right? Like not lowercase g, not like the 9.8 thing. Capital G, which is this number approximately 6.67 times 10 to the negative 11th. So it's a tiny number, but tiny number in units of newtons times meters squared divided by kilograms squared, right? So in gravity, you take the mass of something in kilograms, multiply by the mass of something else in kilograms, divide by the square of the distance between them in meters. So now you have kilograms squared over meters squared. And then you take that whole package and you multiply it by this proportionality constant, G, this universal gravitational constant. And this number that you multiply the whole thing, first of all, will shrink down. It will end up showing you that your force of gravity between any two random objects is going to usually be a really tiny, tiny number. Like you're multiplying all this information by 6.67 times 10 to the negative 11th. So everything gets multiplied by this tiny, tiny number, which shows you why gravity doesn't really start to matter. It doesn't seem to make much of a difference until you're talking about things like planets and stars, and, you know, enormously massive objects. But anyway, you multiply the two masses by this proportionality constant, and the units of this proportionality constant are newtons times meters squared divided by kilograms squared. So the meters squared cancel out, the kilograms squared cancel out, and you're left with newtons. You're left with a tiny, tiny force called the force of gravity that exists between any two objects in the universe, like any sun and any earth, but also any person on earth and the earth itself, and also any person and any other person. Is just so tiny that other forces dominate and end up mattering much more in our lives. But my point here is that the big capital G number is just a proportionality constant. It doesn't change the analysis of any of this, but it does ensure that all the units then end up yielding units of force of newtons, so that once gravity is computed or exists, then it just acts like any other force. It contributes to the F net side of Newton's second law. It ends up contributing to F net and contributing to acceleration, right? Now, so in other words, gravity then acts as a force, and force contributes to just all of our classical mechanical problems, F net equals ma. Same thing happens on the microscopic level between charges. A little bit harder to picture because it's a little bit harder to picture microscopic particles. It's a little bit harder to picture charge than it is to picture mass. But charge acts just like mass, I mean, analogously, in that charges automatically pull and push on other charges in the universe. So charge acts just like mass, except for this one other distinction, that charge can come in one of two varieties, positive or negative, and can thereby contribute to both pulls and pushes in the universe. So let me give you the numbers for how this works. And yeah, we have 12 minutes. Okay. With electrostatics, the concept works exactly the same. Only now pluses and minuses apply. So now we have two different types of charges that can pull in, that can interact with each other. We have positive charges and negative charges. Again, like we said before, if a positive and a negative are involved, then we get as a pull. And if a positive and a positive or a negative and a negative are involved, then we get a push. But numerically now, these charges are measured in a unit called coulombs. Okay, Q1 we generally take to mean, the bigger charge, if there is, I mean, they could be two equal charges, but we're just being arbitrary in general, chances are they're not equal size. And if they are equal size, you still call one of them Q1 and the other Q2. But Q1 is generally the bigger charge, more specifically meaning the source charge. So Q1 is generally what we regard as the charge that, if we're looking at it, is the one generating or creating the push or pull. And Q2, we call, you'll see why we call the test charge, meaning the charge that's there to receive the push or the pull, the charge that's testing the effect of the pull or the push, the charge that's going to accelerate in response to the push or the pull. And so if we were talking like gravity, it'd be like when you're talking about the sun and the earth, maybe the sun is like the source and the earth is like the test mass. Now, to be sure, let's be clear. Newton's third law exists and is true. Also, multiplication is commutative. So I don't want there to be any confusion. Like if the sun pulls on the earth gravitationally, oh, well, then absolutely the earth pulls on the sun gravitationally and by the exact same amount. It's very important to say, right? If the sun pulls the earth, then the earth pulls the sun. And similarly, if some proton pulls on an electron, oh, then the electron most certainly pulls on the proton. But and that's all definitely true and important. But let's also remember from physics 1 that like F net equals ma, meaning the force on me accelerates me. Even if someone's pulling on me, then I accelerate. Now, by Newton's third law, if someone's pulling on me, I also pull back on them. But that's going to cause them to accelerate. That's a totally different free body diagram, different physics problem. I have to choose in any moment whether I'm analyzing or predicting or studying the motion of me or them. They're both happening, but you have to choose like which one you're looking at. So in general, if we're looking at a proton pulling an electron and we're going to study the acceleration of the electron or whatever, then we would call the proton the source and the electron the test. We would call the proton Q1 and the other one Q2. So it's just a designation thing of like what we're focusing on. We're not actually saying that anything special is okay. But now, so we have a source charge and we have a test charge. And I realize we have 6 minutes left. I just want to like lay out these facts and then we'll go. Charge is measured in coulombs. Look, what is a coulomb? Well, coulomb is actually turns out to be a very, very large amount of charge, as a matter of fact. In fact, it's very large and it's sort of an inconvenient unit in some respects, but it's a convenient unit in other respects. But how to relate it to stuff is the good news is that the proton and the electron, as you may know from chemistry, both have the same amount of charge if we measure in coulombs. Like that's a great thing of nature. And that's why atoms tend to be balanced. Like, the hydrogen atom has one proton and one electron. Each one of them has the same amount of charge, just acting in different directions. And so the total charge of a hydrogen atom is nothing, and a hydrogen atom generally is neutral and stable, right? But what is that amount? Well, the amount of charge in a proton is positive 1.60 times 10 to the negative 19th coulombs. And the charge of an electron is negative 1.60 times 10 to the negative 19th coulombs. I'm not saying you have to memorize that number, but that number is always true. That's the charge of a proton and the charge of an electron. And the significance of the number, just to put in perspective, is just to show you that a coulomb is actually a very large amount of charge. Like when we talk about a coulomb of charge, we're actually talking about like, I was going to billion, trillion, quadrillion, billion, trillion, quadrillion, quintillion, right. So a coulomb is actually about 16 quintillion protons worth of charge. Like to have 1 coulomb of charge, you need like 16 quintillion protons. That's a lot. Like the amount of charge that a proton has is very, very tiny if we're measuring in coulombs. You might even say, well, why the heck do we measure in coulombs? And that seems like absurd. Well, the reason is because we first can detect charge and we first can understand it and picture it and deal with it first at the macroscopic level when it's rushing through wires in the form of electrical current. Okay, like I'm not up to that point yet in this lecture, but just to put things together, the minute you start dealing with this in the few labs you have left in this class, you're going to right away be dealing with simulations of electrical current and electrical wires, electrical circuits, because that's what we can actually study and do anything with on a macroscopic level. And all of that was discovered before we retrofitted and retro-engineered and understood that underneath that comprising these big functional electrical currents, there were these little pieces called electrons. Okay, so so it's all sort of like history retrofitting our understanding. 1 coulomb is really the amount of charge that 1 ampere of current delivers in 1 second, as it turns out. And an ampere of current is easier to measure than like an electron. Okay, but 1 coulomb of charge is about 16 quintillion protons if it's positive charge, and 1 coulomb of negative charge is about 16 quintillion electrons. Then the proportionality constant, and I'm watching the clock, I know we have like 3 minutes left. This proportionality constant, K sub E, I'm calling it K sub E because we already have 2 Ks flying in this class. I mean, we have K from Hooke's law in this class already. And we have the K that means angular wave number. That's already confusing to a lot of people. And those are in a similar topic that they come up, but they are not the same, right? The K of Hooke's law is one thing, and it's measured in newtons per meter. And then the K that means angular wave number is measured in radians per meter, totally different thing. I try to distinguish those by putting like serifs on the angular wave number K. But please note, I mean, even at this point in the semester, sometimes that's still like, people don't realize that. We have 2 different Ks already in the class. We now have a 3rd K. I feel bad about that. It's just reality. But so I try to put a little subscript E under this K to make it clear which one I'm talking about here. This is what you might call the Coulomb constant. This is the constant of proportionality in Coulomb's law. It's functioning just the same way that the large G functions in the gravity law. It's just a number that you multiply once you have some amount of charge over here and some amount of charge over there, and you measure in coulombs, you multiply them together, you divide by the square of the distance between them. So now you have one big package of quantities. You multiply all that by this enormous number, this Coulomb's constant. And I know there's 1 minute left of class. You multiply the whole thing by this enormous 8.99 times 10 to the 9th, 10 to the positive 9th number. And this number is measured in newtons times meters squared divided by coulombs squared. So your meters cancel out, your coulombs cancel out, and you're left with newtons, just like the gravity law. So in the end of the day, a proton over here and an electron over here, they pull on each other with an amount that's determined by Coulomb's law, just like the sun and the earth pull on each other with an amount that's determined by the gravitational law. In the end of the day, the Coulomb's law gives you a force measured in newtons. Now you have this force measured in newtons. It can be plugged into F net equals ma, just like gravity, or just like the normal force, or tension force, or friction force, or the Hooke's law spring force. This, once you multiply these numbers together, you have a force measured in newtons that totally behaves and acts in a classical mechanical context, just like any other force would. It is subject to Newton's second law of motion. Just note that the constant of proportionality here is enormous. It's 10 to the positive 9th, whereas the constant of proportionality in the gravity law was tiny, 10 to the negative 11th. That suggests that all other things being equal, and this is where I'm going to stop. I see that it's 1:30. I'm going to say this last sentence and we're done. But just qualitatively put this in perspective, I'm saying if you just put two electrons, literally two electrons, separate them by, say, a meter, okay? You have like two electrons isolated in the lab or isolated in outer space or something. Each electron has a certain amount of charge measured in coulombs. Also, each electron has a certain amount of mass. They do. I mean, they're very small in volume, but and I forgot to write on the board. I'll write next time. But the mass of an electron is like 9.1 times 10 to the negative. Oh my God, how did I just totally forget? 10 to the negative 31 kilograms. Okay, so you got two electrons. I know it's 131. I'm just going to say this and you're done, but if you have to go. But I'm just about to, if you have two electrons just sitting there on the table, they will pull on each other by virtue of gravity. Like automatically, they will pull on each other by virtue of gravity. They will automatically push on each other by virtue of electrostatics. What these numbers tell us is that the electrostatic push between two electrons is way bigger. All of the things being accounted for, it turns out to be like 40 orders of magnitude bigger than the gravitational pull. I mean, so the electrostatic push due to their charges will be way stronger than the gravitational pull due to their masses. And so in the macroscopic world, we actually end up caring about electrostatics a lot more than we care about gravity. We don't really care about gravity until we get into huge objects in outer space that are also electrically neutral. Okay, that's all I have to say right now. You've been very patient. We'll continue on Tuesday. Thank you very much. And I'll stay in case there are questions, but I'm good. Thank you. Have a great day. Yes. Have a great day. Thank you. Thank you.